Let me break this into 2 lines. It's better. All right, so we have a triangle ABC with orthocenter H. BH, okay, so we want to draw the altitudes. D, E, F, G, H. Okay, so X is on BC. Looks like it can be any point. Well, X and BEX intersects AB at Y. We draw BEX and CFX. Interesting. Can we make both of them intersect AB and AC on the same side? So BEX, we want to see where it intersects AB, and CFX, we want to see where it intersects AC. I think we have to extend one of them, is my guess. Like, I don't know for sure, but I think that's true. So yeah, let's extend CA and so these are going to be X and Y. No, so Y and Z. This is Y. And this is Z. We want to show the circumcircle of AYZ is tangent to AH. Hey Glenn, thanks for rejoining us. So, okay, so we want to show that that's tangent. Hopefully it's not just an easy angle chase, but might be. In which case I might find some harder problems for us. And it looks like those circles concur, which might also be an easy angle chase. So X can be any point, which is kind of interesting. Wherever X is, it looks like this
looks like D lies on AEHF also.
Okay.
And that DH and X are collinear.
Interesting. Well, is that true? How can DH and X be collinear? Because what am I missing here? Because E and F are not. E and F are the feet of the altitudes, right? So the circle A. It's not. Okay. We didn't draw the circumcircle of ABC. Interesting. Okay. Let's make a little bit of room here. So yeah, ABC almost looks isosceles, but it's not. So I think that looks a little better. So yeah, do we have like a Miquel point? Because we have so many circles all meeting at the same point. Doesn't it feel like a Miquel point? Just don't see exactly how to do it. But
It does feel, but I'm not also sure. But what I saw is that you can invert at H with radius HE times HB, and then reflect everything around H.
Okay.
And then X would go to D, and circles BXC and CXD would stay the same.
Okay.
So basically that would prove the concurrence of the three circles just apart from ZAY.
Okay. And that one, so Nguyen says we can use Miquel's theorem to prove AEF passes through D. Oh, okay. Maybe not then. So, okay, so we can use inversion with basically radius square root of BH times HE. So it swaps, okay. So the first circles we draw are like, sorry. So we want to show it swap. So we first draw these two, and then we show that that inversion would swap X and B, because it swaps B and E. It swaps C and F. So we want to see where it would take those circles. So if it swaps B and E, then it would take this circle to we want to show it takes this circle to this. So yeah, how do we show? Okay, we know it swaps D and X, and we know it swaps B and E. We want to see what it does to the circle AFHE.
AFHE goes to line BC.
Goes to line BC, because, okay. So, and so we want to show D lies on that circle, but we know it does because D goes to X and BX and C are collinear. That's kind of the idea, right?
Yeah. Also, I just noticed that you could use Miquel theorem, the one for triangle.
In what triangle?
For triangle ABC and points X, Y, and Z.
Okay.
To show that D lies on AZY also.
Oh, so okay. So then that would show both circles. Okay.
Yeah.
So
You remember Miquel theorem for triangle?
yeah. So okay. Interesting. So consider an inversion at H with radius root BH times HE. I think it's HF, right? It swaps B and E, C and F, and D and X.
You should maybe write that you reflect everything around H after the inversion.
Why? Oh, so that it doesn't, yeah. So it's like followed by a reflection across H. Okay. So it's like a negative, yeah. It's a good point. Or like a negative inversion. It swaps B and E, C and F, and B and X. So That means it sends the circle AFEH to the line BC. And that means it sends X to D. And that means that ADFHE is cyclic. Okay. And then we can finish it off with Miquel. That's what you're saying, right? Because if you look at, is it BFEC is what we're using Miquel on, or is it some other?
Triangle ABC and points X, Y, and Z.
Okay. So the circumcircles of BXY. So sorry. Because three of them concur, or because two of them concur, the third has to concur. Okay. So yeah, we have BXY, CXZ, and so AYZ has to concur. So by Miquel's theorem, I think it was BXY, CYZ, and AXZ concur. And that means that, so this should be AYZ, CXZ. So that means that AZBY is cyclic. All right. Should we draw that in? And then it's probably an angle chase, I'm guessing, right?
Yeah. You prove that DAH is DZA.
Yeah. So, yeah, DZA is DYF. Which DYF is DYB is DXB. Yeah, at that point it should be pretty easy because BC is parallel to the tangent at H. So yeah, and then that would be DAH. So okay, so let's write it out. So DZA is DYB. I don't know if there's an easier way to do this, but DZA is DYB, which is DXB. B, and I'll just say it like this. So DXB is the angle that DH makes with this, where L is the tangent to make a comma to AFHE at H. Which is angle DAH. So that implies that the circumcircle of AYZ is tangent to AH. All right. So yeah, these problems, yeah, easier than I thought. We have about an hour left, so do you want to look for some harder problems, or do you want to try these? What do you think? So yeah, we can either try this one or this one. Or we can look for other problems. Either of you have a preference. Otherwise, I could just go on with this one. All right, I'll try this one. So we have a point on the circumcircle of ABC, and this is interesting. So we want A, B, E, and F to be cyclic. All right. So E and F are on AC and AB. And M is the midpoint of BC. And show that if DM, BE, and CF are concurrent. Okay, so BE and CF, you give it a name, G. Either that's on the circle or EF is parallel to BC. So it's saying that DG and M are collinear is equivalent to G being on, yeah, it doesn't say which circle. That's kind of weird. Show that if DM, BE, and CF are concurrent, then either, does that even make yeah, okay, so okay, in this figure it looks like EF is parallel to BC. Let's move E around a little bit. Like, okay, so I mean we could kind of work backwards. What if I make this a tall triangle? That. I don't understand this. Yeah, it's on the circle. What would that look like? They're trying to say G lies on HBC with orthocenter H. Okay. Let's see. Oh, that's for the circle part. Okay. So oh, because are you kind of just reflecting things? Is that how you got? So CG and BG cut AB and AC. I'm a little confused. We should take G lies on HBC first. So are you saying first create a point here and then So like when does G lie on HBC? Is maybe the problem is that D is like should be over here instead. Why don't I redraw this, but instead of rays, I'll make everything lines, because I think that might be what's confusing us. So everything is going to be lines, and then I'll hide everything. So D will be on the circle, and A, D, E, and F are cyclic. E is on AC, so let's do it like that. That's E, that's F, M is the midpoint BC. So we have DM, DE, and CF. And let's see. So if I move D here, okay. So BE and CF, I want to draw this point right here. So G, and then okay, so if D equals A, D equals A, then we have kind of a Cheva's theorem configuration. But the other one is where D yeah, I don't understand the other configuration. Does it let's see what when just said. Take G. So if I let H be the orthocenter, and I mean that yeah, it's the same as reflecting the circumcircle. But how do you make G on HBC? Are you saying kind of like this? You should take H and G. Okay. Then if that's true, does DM, DE, okay, then they would concur on the circle. I see what you're saying. Interesting. Yeah, it's weird they say the circle. Oh, the circle ADEF. I don't know why I got so confused. Okay. All right, so those, it works in those two situations. We just have to show like those are the only situations. I see. So either D equals A, and then you have, but if D equals A, then the circle ADEF is just, yeah, AEF. And then if, and you have the parallel situation. Otherwise, you have this. So yeah. So yeah, it's just kind of like two degenerate cases, right? It's kind of weird. Yeah, let's first look at this situation. So I think at this point I can start making things segments. Hopefully it won't mess up too much. So this will be a segment, and this will be a segment. This, this, and this. Okay. So how did you know that G would lie on this circle, BHC? So it's the reflection of ABC over BC. But did you just kind of play around with the diagram? Like, how did you know that that would work? Yeah, how did you know that G would lie on this circle when it happens? Was it just something you noticed when playing with the diagram?
That's by the problem statement, right?
Well, in the problem statement, it says it would lie on A, D, E, F, but not on BHC, right?
Yeah, but you could angle trace.
You can angle trace.
Angle BGC is 180 minus angle A.
Okay,
So that would be it.
that makes sense. Now let's see. So, okay. So if it's, so we know if it's on the circle. So yeah, we have to first assume they're concurrent, and then show that that would lie on the circle.
I noticed that we would want to show that an inversion at M with radius MB takes G to D.
Takes G to D.
Yeah.
Okay. Yeah, it's the direction we have to prove. Yeah, I agree. All right, so that's where they're tricky. I'm sure whoever created the problem knew very well that one direction is easier than the other. So yeah, we invert about M with radius MB. And we want to show it takes G to D. Let me think about that. So that means the power of M with respect to that circle is MB squared. So yeah, what we could do is, hide this circle for the time being. We're assuming that MG and D are collinear. And oh, we know ADEF is cyclic. We want to show G lies on the circle. Is there like a symmetric way to do this? What we could try to do is we could try to show that CF cuts segment MD into the same ratio that this circle cuts MD. Because then we're not assuming they're concurrent. So well, no, we assume they're concurrent, and then we want to show that it's on the circle. Yeah, it's a little tricky. This problem just seems like a lot of special cases, especially since you have to like prove two different things like this. Do you guys like this problem? I don't like this problem that much, really, but
Me neither.
all right, yeah, let's do something different. So let's see what we can find. So here's Taiwan TST. So yeah, that one. I mean, we just did this one. It's too easy to be a number 5. Yeah, these look a little bit easy. I mean, it's round 1. Let's check round 3. I don't know.
How about we do some IMOC from previous years,
Okay.
like some harder one?
I've done them on my channel before, but yeah, I'm sure we don't remember all of them. So yeah, here's an if and only if problem. It's a G2, so maybe it's might be too easy.
Yeah, we can do G11.
G11.
Yeah, maybe.
Let's see. Need a C. Okay. Projections of B. Okay, you're projecting everything onto the Jargon lines or whatever you call them. That's kind of complicated diagram, but we can do it if you want for G11. So yeah, look through these problems and yeah, let me know which one you like best. we're changing to another one. Yeah, we got bored of it. G9 looks kind of interesting.
Yeah, it does, but G9 to me looks impossible.
It
To be
looks really
honest.
hard. Yeah.
Yeah, like very hard. How about G7? It looks kind of okay.
Okay. All right.
I mean, we could try G9, but if we had more time, I think.
Yeah. All right. Close
Maybe on the
your
next
eyes
session.
so that you don't see the solution. I'm just trying to copy the latex. So, okay. All right. Okay, so I'm just gonna take this and rewrite it. Let me just break this up. Wait, was this actually the problem? I think it was, right? I feel like it's been too long since we've done like in circle problems. So we have DEF, DEF, tangents at E and F. Okay, so let's draw the in-center, and it's going to pass through circle AEF. The tangents intersect at the mid. I think the tangents intersect at the midpoint of BC, right? Is that right? That's that famous theorem. Let's see if it's true.
That's in the orthocenter.
Oh, sorry, that's the orthocenter, not the center. Okay. So, yeah, this almost looks like there's two lines. It's weird. I don't think I drew two tangents, but all right. So they intersect at P. Didn't you kind of say you found a problem with these two tangents or something? Or maybe it was like the one you were thinking about submitting and then somebody else found the same problem?
It's a bit different.
Okay. So those intersect at P. Almost looks like FP and P are collinear, but they're not. So weird how it keeps flipping. Yeah, I don't. Is that a bug in GeoGebra? Because there shouldn't be. It looks like a bug. Let's see. Okay, so yeah, I'll give you the link to it. Oh, he was just asking. Okay, all right. X is on BC such that EF, DP, and AX are concurrent. Interesting. Let me make things a little nicer. Draw ray. That's interesting. Oh, we have to do this symmetrically. That's annoying. I wonder if there's a way to think about this without having to draw everything. So what does it mean if X, so we have 3 points, X, Y, and Z on the sides. We could kind of, like using Menelaus, can we think about it a different way that would, like, can we say something about the ratio bx over xc so that when we use Menelaus for x, y, and z, it would make it collinear? You kind of see what I'm saying? Like, do we really need to draw y and z? Oh, he's Serbian. So let's see. So if you have a triangle ABC, so y is on the only tricky thing. So if we had like 3 points x, y, and z and they were collinear, we would have this over this times this over this times this over this. So yeah, can we find bx over xc and then use Menelaus? We could try using projective geometry, so we could try letting EF meet BC at a point, and then projecting those points through A onto EF. It's one way to do it. So yeah, I missed this line right here. But basically, like one thing we could do is draw the foot of the angle bisector. So, oh, P lies on the angle bisector. So basically, this is the midpoint of EF. This is the foot of the angle bisector right there. Oops. Probably need to make it bigger. And so we have BXJC, that cross ratio is FGHE. From there, maybe we can get BX over XC, and then we could use Menelaus. That's kind of what I'm thinking. So we have FGHE. Can we project through P?
It's better to project through D.
Through P or
through D.
D. Okay.
Onto the angle bisector.
Okay.
Then everything is like quite nice.
Okay, so we need to project E and F through D onto the angle bisector. So then we have this point K, and we have this other point L. So FGHE is LK HP or PLKH. Stefan Chebez. That's interesting how like when you speak a language, you think that those are like all the sounds that you can make. And then like other languages have these other sounds that you're like, oh, I didn't know there was like another sound you can make. But yeah, English has a lot of ones like this, the TH sound, and this. I don't think most languages have that. Okay, so PKLH, we want to find that cross ratio in terms of like the sides of ABC. I wonder how we can do that. So IDJ is 90 degrees. We know that. Let's check something. PLKH. What do we do with that? So I was going to say we have like EH over EF times FB over DL. LK over KH equals 1. What's FD over DL? So FD we know, DL. BX over CX. That's what we're trying to go for. So yeah, I think we really like we just need to think about FG over GE. This reminds me a lot. We did some problem using DDIT where we had like tangents like this, and then we like intersected it with like a side. Like there was this one problem that looked a lot like this, and we solved it using DDIT. But I don't remember exactly how. What if we project FGHE through I instead? I just don't know where G would go to, but because EF and EI and FI would be perpendicular. Could this be the Could this be like the X touch point? I don't think so, but it would be interesting if that were true. Yeah, I don't think it's true. Reflect D over N. Yeah, it's not the X touch point. But EF and IF and IE are perpendicular to the sides. I guess we could say FG over GE is DF over DE times sine FDG over sine EDG. We could try that. We have PHIA. And then project it onto EF. Okay. So, but what do we project it? We project it through D.
Oh, that is really smart. I didn't notice that. You project first through D onto EF.
Okay.
And then you project through A onto BC. And you get basically everything really nice.
Okay. So you start with what Nguyen just said, or my Nguyen. So
Yeah, the PHIA is harmonic. That is really important.
PHIA is harmonic. That's because H lies on the polar P, and then if you project through D onto EF, you get GH. So do we take the intersection of DA and DI with EF? Okay. All right. Interesting. So yeah, DI, you're just going straight vertical. Okay. And AM is actually a median, right? Is that the Iran lemma? Like AM bisects BC, I think. Is that right?
That's true, but it's not called Iran lemma. I don't know if it has a name.
Okay. All right. So then we have G, M, N, okay, so PHIA is H, we have H, M, N, and G, H, M, N, G. Okay. And then those 4 points we project through we project it through A. Is that the idea? And then
Through A onto BC.
Okay. And it goes to the midpoint. And so then basically if we used basically everything in that expression is like symmetric with respect to A, B, and C. And so it's kind of like we use Menelaus, we think everything would cancel. That's kind of the idea, right? Okay. Because J would be the foot of the angle bisector, O would be the midpoint of BC. D is, we know it, yeah. Everything would cancel really nicely, actually. Yeah. So I'm gonna write that up. So H lies on the polar P with respect to AFIE. I'll say label the points are shown. H lies on the polar of P with respect to AFIE. And that means that PHIA is harmonic. And then we take that and we project through D onto EF. Then we have GHMN is harmonic. Okay, and then projecting through A onto BC. Then we have XJ, XJOD is harmonic. And okay, so we want BX over XC. But the idea is if we have XJOD, we could calculate that ratio in terms of it. I think that's the idea, right? Is that sort of what we were thinking? If we know this cross ratio, then we would know BX over XC. Seems true.
Do you know how to get BX or XC?
I guess you're asking my, right?
Yeah. I mean, we have this nice harmonic bundle, but to me, it is still not clear how to get BX or XC.
Yeah. So maybe we could try to calculate B like JOC and BXDC and combine them somehow, but yeah, it doesn't seem that easy. So yeah, it might come down to like a calculation.
Oh, I think there is something which might be useful.
Okay.
Yes, we have that XD GEO is harmonic, intersect OI with AD.
OI with AD. Okay.
That would by IM lemma be just midpoint of AD.
Okay.
So by harmonic bundle, X, Q, and M are collinear.
Okay.
So basically, X lies on the median, M a median of triangle AMD.
Yes.
That looks useful.
That X is in the median of AMD. Yeah. I agree, that does look useful. Yeah. So now we have probably a much better way of understanding point X. I like that. Let's see. So yeah, we still want dx over xc. How can we use that? That's a median. I kind of want to draw this point right here. Oh no, I don't think it does much.
Maybe now it would be like useful to draw the other symmetric points, since now we can do it with not much construction, just to
Yeah.
see what that line is.
Yeah, so we could draw all these perpendiculars to the sides and then draw like the medians.
Well, you need just one more.
Okay.
Drawing all three is like not important.
Okay. So yeah, do these concur? That would be interesting. No. But so yeah, we have where this meets it. And then we could draw like BE, and the midpoint of BE. S. I don't think S lies on GD. So basically it's where RS meets AB. I think that's right. Or wait, is this problem asymmetric? No, we want to see where RS meets AC. Sorry, I don't know why I was thinking AB. So at point. This might be like Y, for example. So this is the line. And yeah, don't know if there's anything special about it.
Shouldn't you intersect RS with AB?
AB.
AB,
So right here.
yeah.
Well, because I'm taking the midpoint of BE. Let me think about it. I thought it was AC because I was doing. Oh, I think yeah, you're right. But then I did the wrong. Then I need the midpoint of CF, not BE. So I did it wrong. So I should draw CF and take the midpoint. And then see where RS meets it. And that would be point Y. It'd be interesting if the line is tangent to the end circle. Oh, maybe it passes through P. Doesn't look like it, but it looks like it might be tangent. Yeah, that's kind of interesting. So this line that we want is actually tangent to the circle.
That is really interesting.
Maybe it's tangent at the Feuerbach point or something.
Won't be surprised.
Let's see. So we have this, this, and this. And what was the midpoint? Oh. Oh, it looks like it is. Yeah, it looks like this line is tangent at the Feuerbach point. That's interesting. I would not have expected that. But yeah, I don't know too much about the Feuerbach point. But that is an interesting piece of information.
We must call Serdar right now to
Yeah,
help us.
he likes it, right? They're really, yeah, those look pretty tangent to me. So basically, you'd want to show that x, y, and the Feuerbach point are collinear. And you could do that, that would solve it. What's the midpoint of x, y? Okay, it's not B. Yeah, now this feels even harder. So yeah, we might be able to bash it with this. Let me write it on a sheet of paper. Oops, what did I just do? That's fine. It's just this, yeah, CF. And what is that? Oh, RF. I just need to draw RF. Okay. So yeah, let me write out XJOD as an algebraic expression. So XD over DJ times OD OJ over OX. So XD is BD minus BX. DJ is BJ minus BD. And then OJ CJ minus BC over 2. And OX is BC over 2 minus BX. Okay. Yeah, it would take a while to take this and make it work, if it's even possible. But yeah, it's interesting that we saw it pass through the Feuerbach point. Yeah, I know there's a lot of properties of it. Yeah, I just don't remember all of them. Let's see. So yeah, maybe so XDJO. Maybe we could project through M onto AD instead of AP. So then you get QD, QDO. Oh, wait a sec. It's the same as saying that MJ is parallel to AD, right? Well, wait, is MJ parallel to AD? That makes it seem like it. Yeah. I think I did do yeah, so it's kind of interesting. So the foot of the angle bisector and point M, if you connect those, they're parallel to AD. Maybe we can do something else with GHMN. Maybe not. We have 7 minutes left. We could try a super easy problem in 7 minutes if you guys want. But yeah, I don't know if we'll solve this one. What other problems did I have? Let's see. I had one other, oh, this one, which we didn't like. Okay. Yeah, let's just finish with this one. We're almost done. I'm going to look at properties of the Feuerbach point. Kind of cheat here. Properties. It lies on the line through the centers of two tangent circles that define it. Obviously. So yeah, we could draw the 9-point center. Okay. Yeah, we need Sir Dart here. Let's see. So this is a 9-point center. Obviously, those are collinear. So yeah, I mean, basically,
there is one theorem that here the Feuerbach point will be anti-Steiner point of OY, but not OI from this picture, but O is the circumcenter of ABC.
Okay.
So it would be anti-Steiner point of OI with respect to triangle DEF.
Okay, so like Z is the center. Okay, so if we have triangle DEF and we look at line ZI, it would be the anti-Steiner point of that with respect to triangle DEF.
Yeah.
Interesting. So you take that line, which passes through the orthocenter of DEF. So that line ZI passes through the orthocenter of DEF.
Yeah, it is the Euler line of that triangle.
Okay, I is the circumcenter. Wait, so ZI is the Euler line of DEF, or Z is the circumcenter of ABC?
Yeah. That's true.
Is that obvious, or?
Not completely obvious, but well known. You just for proof, you just invert around in circle.
Okay. And so if you take that line and you reflect it over each side, then it will pass through B. That's pretty fascinating. The intersection of OI and BC has some connection to this problem. Do you see something? Or so I'll draw it. I'm guessing you mean this point, right? We could take the midpoint of arc BC. Oops. All right. Oh, the small arc. Whoops. So yeah, it's gonna lie on AP. Oops, sorry. Okay. Then project C1, X through X, the J and O to the circle. This is interesting. This is not what I would have expected. So, oh. So this goes to the midpoint of this arc. And then this, I'm not sure where it goes, but it looks like these concur. So yeah, these lines are so close together. I would not have thought. All D prime, the reflection of D over EF. Then A D prime passes through A1. Interesting. This is fascinating. Okay. Cut O at some point. Okay, so basically you're saying draw that whole ray. See where it cuts the circle. Let D prime cut EF at Y. I'll call it Y. AY, there's so much, wow, this is a complicated diagram. AY puts the circle at Z. B1, oops. D1, D, and Y are collinear. Or I think you mean D1, D, and Z. Okay. I just don't see how we use E1. That's the only thing. Oh yeah, okay. Yeah, there might, the one thing I just don't see is how to use. We have A, D, D prime, J, Z. Okay. AD, let AD cut O. At T. So G1, TZ, C1 is harmonic. Okay. So yeah, so that's harmonic. Then yeah, G1, TZ, C1. So DG1 passes through E1. That's where we use it. How does that follow? Is it is that because is it first we have XJ and DO? Where is X? X. Oh, this X, sorry. And then we projected to O. And then E1, F1, A, D1 is harmonic. You're projecting everything through D. Oops. Sorry, I didn't mean to do that. So that's harmonic. And G1T. Yeah. Okay. XB or XC is equal to E1B over E1C. Okay. E1B over E1C is DB over DC times G1B over G1C. Wow, this is amazing, this solution. This is incredible. So yeah, we're over time, but this is just really cool. So A1's and A1 is kind of defined symmetrically. So it's, yeah, okay. All right, so I'm going to stop here, but this is a really, really cool solution. Yeah, thanks a lot for bringing it up. And so yeah, I'm glad you were able to share this. Yes, it is. It is definitely very amazing. All right, so yeah, thanks for participating today, and for everyone watching on YouTube, thanks for watching. So if you want to join us in the future, feel free to email me at mgreenb801@gmail.com. It's in the description of my video, and we meet every Sunday at 8 a.m. US Central Time. So thanks again, and have a great day.